In 1859, John Tyndall first proved the greenhouse effect, the temperature increasing effect of gases such as carbon dioxide, methane, nitrous oxide, and ozone. It's not until 1960s when National Oceanic and Atmospheric Administration, or NOAA's laboratory, developed the first of its kind climate model that we understood and predicted global warming. By the 1990s, it was apparent that the Earth is warming up. 2 weeks ago, we found out that the natural cycle of the Gulf of Alaska is increasing our ocean's acidity, and the Australian wildfires triggered massive algal bloom. Last week, the worsening global warming has decreased the food webs of polar oceans once again. In the same warming Earth, with the aid of technology, more and more humans are turning to their screens for direction. Apparently, Google Maps can tell you which route will lead you to your destination the fastest, given your current speed and the level of traffic on all available routes. Stunning, isn't it? What helped us predict the catastrophe of a warming Earth 6 decades ahead of its time, and helped us navigate in the labyrinth of urban cities with ease and efficiency nowadays, are two technologies that relied on one thing: mathematical models. Hello, students. Hello, Debesimscat. I am Mark J. Aquilio, and today we'll talk about an introduction to mathematical modeling. In here, we'll learn about what models are, what the types of models are, what mathematical modeling is, what advantages one can have with mathematical modeling, and what objectives can we achieve by mathematical modeling. Models describe our beliefs about how our world functions. You see a globe before you, and it describes how you think the world looks like, or how it's tilted on its axis, or what happens to each region as it revolves around it. Globe is a model. A model can come in many shapes, sizes, and style. It's important to emphasize that the models are not the real world. They're just human constructs that help us understand real-world systems better. You see a tiny model of a car, but you don't think it's a car. You can't ride it, and it cannot transport you anywhere. It's a human construct that help you understand a real car a bit, how it looks like, and how it moves. Depending on your sources, the number could vary, but generally, there are 5 model types. We have the conceptual models, made out of verbal or graphical representations of how a system works. We also have graphical models that helps us understand data quickly through visuals like maps, charts, and diagrams. We have physical models, or three-dimensional models that enable us to interact with it by touch. The 4th type of model is computer model. It represents complex processes of a system using a computer. This is a powerful model, built with algorithm based on math models, and can even perform experiments. Lastly, we have mathematical models, or descriptions of how the real world functions, only in the form of equations. In mathematical modeling, we translate our observations and beliefs of how the world functions using the language of mathematics. Of the 5 models presented, we're going to explore mathematical modeling in this class. If used correctly, mathematical models are powerful tools that could assist us in our day-to-day life, can even help us predict the future with relatively remarkable accuracy and precision. The advantages of modeling in mathematics are the following. First is mathematics is a very precise language. Say you measure an apple once and found that it weighs 100 grams. You can measure as many times as you like, but you'll always end up having 100 grams, or at least very close to it. In mathematical modeling, this precision is important because it tells you that when you describe a system using the language of mathematics, you'll always end up having the same result no matter what. If there's a deviation, it's minor or insignificant. Mathematics is a concise language with well-defined rules for manipulation. Newton's law of motion, for instance, the second law of motion, is but a centimeter long, or even shorter depending on the font you use. If expressed mathematically, it's F equals m times a. Yet it describes precisely the relationship between the force exerted by the object with the product of its mass and its acceleration. Or take the famous Friedman equation, dubbed as the most important equation by Forbes magazine. Around 2 inches long, it describes with remarkable precision the rate of the expansion of our universe. All the results that mathematicians have proven over hundreds of years are at our disposal. That's the second advantage of mathematical modeling. When Einstein worked as a patent office clerk, every day he sits around the mathematical models being applied for patent. This job only gave him time to revel on the marvels of the universe, but it has also sharpened his skills and inspired him. First, he published the photoelectric effect. Then he went on to writing a math model for the size of an atom, way ahead of his time, and then ended up with the revolutionary E equals mc squared. Now, with the advent of the internet, all math equations proven over the years are available at our disposal. Lastly, computers can be used to perform numerical calculations. Whenever we build mathematical models that are too complicated to solve manually, we can also turn to powerful computers to do the equations for us. Currently, the world's fastest computer, Japan's Fugaku, is churning 415 quadrillion computations a second in search for the cure for COVID-19. Now, what objectives can modeling achieve? It has 3 objectives. First one is it develops scientific understanding. Using what we know about a system expressed in numbers, we can identify what we know so far and what we don't know yet. Until the early 1920s, we've always believed that the universe expanded after the Big Bang. The expansion is slowing down because of the gravitational pull of all matter in the universe, and eventually it will collapse back in a big crunch. By plotting our observation in the form of numbers, we found out in 1926 that the universe is expanding, not crunching down, or we're still in a state of expansion. In 2016, looking at more recent data in numbers, NASA and ESA, or the European Space Agency, reported that the universe is expanding 5% to 9% faster than we initially thought, which made us understand the science of our universe further, even coming up with the idea of dark matter and dark energy. Second objective, to test the effect of changes in a system. Wen Wu, an assistant professor of mechanical engineering, worked with 2 professors at Johns Hopkins University. They developed a mathematical model to estimate the risk of airborne transmission of respiratory infections, including COVID-19. With the model, we can now test the effect of a change. Say, We can adjust the duration of a person's exposure to COVID patient and see how it affects the rate of infection without risking a real person to expose himself to a real COVID patient. Lastly, mathematical models aid decision making. By looking at a stock market graph and using a math model to predict the movement of the prices, one can describe whether to buy or sell with precision, thereby increasing his chances of winning a profit than losing an investment. That ends our lesson in the Introduction to Mathematical Modeling. I'm Mark J. Aquilio, instructor for mathematical investigation, problem solving, and modeling.